Hello, everyone. My name is Kolotov, and I am from TokenBridge project. So today we will talk about a tool we developed recently to allow you to transfer any ERC20 token from the Ethereum mainnet to the xDai chain without any additional contract deployment from your side. This tool was built on top of arbitrary message bridge technology, and historically we are building bridges a long time. First of all, it were bridges for some dedicated pair of tokens like POA token or DAI token. But after that, we started thinking why we just start transferring anything from one chain to another chain, any message, any information. And we developed arbitrary message bridge eventually. So arbitrary message bridge allow us to transfer any data from one chain to another, as I said. And so in order to achieve this, one contract need just encode method call and data for these methods, and transfer this data to the arbitrary message bridge contract. And the arbitrary message bridge contract will call this method on another side of the bridge. So it will be called in another chain. So technically, it look like presented on this picture. So as I said, someone would like to send something from one chain to another chain. They need to encode the data, including the method descriptor, and arbitrary message bridge will transfer it. So it will emit events, and Oracle's arbitrary message bridge oracles will pick up this event and send these confirmations in form of multi-sig to the bridge contract on another side, on another chain, and this contract will execute eventually the target contract, right? So arbitrary message bridge consists from contracts from the oracles, as I said. We also have some health monitoring tool, deployment script, and last thing we developed recently is arbitrary message bridge live monitoring tool, which allow users to get status of the transactions they send through arbitrary message bridge. So in order to develop the contracts which will use the arbitrary message bridge, we call these contracts mediators. You could follow the instructions on our documentation page. So, and we already have several mediators to transfer ERC20 to ERC20. Tokens, to transfer native tokens to ERC20 tokens. We even tried and experimented with NFT tokens like CryptoKitties to transfer them from one chain to another. And as I said, our recent deployment is for multi-token mediator, which allow us to transfer any token from one chain to another. So the main idea here is that user just transfer a token by sending them to the mediator contract, and the message will be with this information will transfer to another chain, and another contract, another token contract will be deployed at that chain. So for example, if we transfer some token from the Ethereum mainnet to xDai chain, so we will at the end we'll have two token contracts. One the original contract on the Ethereum, and another one RC677 contract on another side of the bridge, so in the xDai chain. So as you said, so the user need to perform two actions. The user need to approve the mediator contract to send to transfer tokens. And after that, the user initiates token transferring by calling real tokens method from the mediator contract. Mediator contract get name, symbol, and decimals from the original ERC20 contract, and transfer all this information together with amount of tokens should be transferred to another side of the chain. And there, the contract, as I said, the new contract deployed, and the corresponding number of tokens is minted. So later, user don't need to. So later, the new contract will not be created, obviously. So if the user would like to send tokens for existing pair, so it will lead that just another message will be passed through the bridge, and new tokens will be minted in the xDai chain. And definitely the user could withdraw tokens from the xDai chain. So for this, they need to call transfer and call method from the token contract. And the corresponding number of tokens will be burned on the xDai chain, and the message will be passed to the bridge on another side, so on the Ethereum mainnet, and the corresponding number of tokens will be unlocked eventually in the Ethereum mainnet. So as you see that when these tokens are transferred to the xDai chain, so these tokens could be transferred there to any other users, and any user could withdraw tokens back to the Ethereum mainnet. So, and that's why it is very useful. So what else we have on this pair of mediators? So we could not only use approve method, but if the original token is ERC677 or ERC827 token contracts, so they can be relayed without approving. So they can be relayed by calling transfer and call method. Definitely, in the xDai chain, we created such kind of token contract. We use such kind of token contract to deploy new token, which is extended a bit. So user could use just transfer method to withdraw the token. So they don't need to call transfer and call. And it's quite convenient to just use transfer method to withdraw token back to the Ethereum mainnet. So, and more functionality we have, like limits, fees, token registries, token registry, which allow you to get the contract on the Ethereum mainnet if you have just the token address on the xDai chain, or you can get the token address on xDai chain if you know just the token address on the Ethereum mainnet. Okay, so as I said, this contract was developed recently, and we already deployed it on Ethereum mainnet. So we already deployed this pair of mediators to the Ethereum mainnet, and everyone could start using this in order to, solve this high gas fees issue if it is, crucial for your application just now. Okay, and let's try to do some demonstration how it works, but not on the real chain because this demo could be quite slow, and that's why let's use the testing bridge we have between Kovan and Sokol. Okay, here is my browser, and we see the first mediator on the Kovan side and another mediator on the Sokol side on also presented in the browser. So I also deployed 2 tokens before this demo. One token is EDC1 and another EDC2, and let's check that these tokens do not exist in the so-called chain. So we can check that we can find some token, right? Okay, but we can not find, for example, EDC1 or EDC2. Okay, and let's try to transfer it from one chain to another. First of all, we need to address of mediator to allow this mediator to send tokens from one chain to transfer tokens. And let's approve, sorry. And let's approve this mediator to transfer tokens. Okay. Then let's transfer these tokens, also connect the wallet. And we will say that, okay, we will transfer this amount of tokens to another chain. And let's check the transaction. Okay. Let's one more time. Let's try one more time. Okay, this is our transaction, and we can use ALM tool to check the status. Okay, we see that one of the validators confirmed the transaction to be transferred. In fact, we have just one validator, and the status of the request success. So let's find the token on another side, EDC1. Okay, new token appeared. We see that, okay, this is our tokens. This is our token, and we see that these 50 tokens appeared on this side. And also you can find, okay, let's try to transfer another token. Okay, repeat the same actions, proof, and the same amount, why not? Okay, sorry. So now we need to transfer these tokens. This is another token contract. Okay, this is another token contract, and we will transfer it, right? Okay. Let's check the transaction. Okay. Let's check this transaction in LM tool. Wait for its confirmation in the xDai, sorry, in Circle chain. Okay, it also was transferred successfully. It needs some time, okay, but let's check that the token appeared too. Right, new token appeared. And in fact, that we have 50 tokens transferred. And let's return to EDC1 one more time. We recently introduced the feature in the Block Scout, which allow us to see that the token was breached from the Ethereum mainnet, and you will see the link to this token on Etherscan. Okay, so hopefully I will have a time to transfer this token back. This is our address. Let's switch to Sokol testnet, add token, and try to transfer it to the mediator. Okay, this is our mediator. Let's try to transfer it to the mediator. Oh, sorry. Example 30. Okay, this is our transaction. Let's check it. And yeah, it should take some time. Okay, it was transferred, and let's check. Okay, in Coven testnet, we have okay. Yeah, we see that less than 30 tokens were transferred because we have some fee on this bridge for testing, and yeah, we see that the bridge works successfully. Yeah, this is addresses of the Coven mediator, testing mediator contracts, and yeah, thanks for your attention. Visit our sites to get more information and contact us if you have any questions. Thank you.
Hi, I'm presenting on how ENS complements DNS. My name is Brantly Millegan. I work for this nonprofit called True Names Limited, and we are the de facto managers of the open source project, the Ethereum name service. There's more information about us. I'm going to first talk about kind of what ENS is, and then how ENS works, and how it complements DNS, and then how to integrate ENS. So ENS, of course, stands for the Ethereum name service. So what does this mean? So how is it a name service? Actually, we're going to start with the second part. A naming service is just a lookup system. People always overcomplicate this. Just you provide a name, it provides you with information. Your computer might then do something with that information, but that is separate from the naming service. So why do we have naming services? It's because computer identifiers, which work really well for software, are not easy to read by humans. And what's easy to read for humans is not easy to read for software, right? Because human language, it's difficult for computers to understand that. And computer identifiers, it's a long string of numbers and letters, easy for software, but hard for humans to understand. So ENS, just has names, has owners of names and records that can store any information. If you have a name, you can look up and retrieve its records and then do something with that information. Now, this is very important to understand. Let's say you're using it for a cryptocurrency address. ENS provides your wallet with the cryptocurrency address, and then your wallet sends that transaction. Some people think ENS sends the transaction on. It doesn't. This is how we're able to be on Ethereum, but support any cryptocurrency. It's because we're just storing the crypto, let's say the Bitcoin address, and then we give it to the wallet, and the wallet sends the Bitcoin transaction. So why is it called the Ethereum name service then? It's not because it's a naming service only for the Ethereum ecosystem, but because it's a naming service built on Ethereum. So the logic and records are stored on Ethereum, but it can store information relevant to anything. So obviously other cryptocurrencies, It can store an IPFS hash. It can store your email address. It can store anything you want. And we use Ethereum, though, because we think it's the best blockchain platform. And I'm not just playing to the crowd here. I really think this. It has high security and decentralization, obviously. It has all this ecosystem infrastructure built out, like MetaMask and other things. There are standards we can take advantage of. We can take advantage of its programmability and the fact we can interact with other smart contracts on Ethereum, which is really powerful. If we, for example, had our own dedicated blockchain just for naming, we would lose out on all of this. So this is why we are on Ethereum. So ENS uses Ethereum to serve the internet, including and beyond the Ethereum ecosystem. That's the message I want you to take from that. And our goal is to make ENS, and therefore Ethereum, by the way, because ENS runs on Ethereum, a basic piece of internet infrastructure used widely by people, whether they are part of the blockchain community or not. This is our goal. We want to do this by complementing the DNS tech stack in parallel, expanding the capabilities of the existing DNS namespace, focusing on use cases not served by DNS, in some cases not possible in DNS. So we're not trying to do normal websites and email and things like this right now, although we can do that, just because DNS does that well. But we're focused on use cases like cryptocurrency addresses and decentralized websites, which DNS is not suited for. So how does DNS work? Key thing to understand is that we have no servers. We don't run any key infrastructure for ENS. It's entirely a set of smart contracts on the Ethereum blockchain. And so that means anybody can use it. You don't have to use our special API or anything like that. We're not a gatekeeper. This just kind of explains more. There's three main types of smart contracts: the registry, which just holds all the names and the owners; the resolvers, which holds all the records; and then the registrars, which allow people to register names. Of course, resolutions and lookups don't require a transaction because you're just looking up on the Ethereum blockchain. You just have to have access to it. This is what ENS records look like. So we have an address record for an Ethereum address. We have other addresses records for just other cryptocurrency, any arbitrary cryptocurrency. And Ethereum just kind of has that privileged place because we're on Ethereum, and that makes sense given a lot of the dApps that people are using and things like this. We have a content record where you can put an IPFS hash, a swarm hash, or even a tor.onion address. And then we have text records where you can put any arbitrary information. In fact, projects can create their own record type if they need to, very easily using text records. And then we also support DNS records for some use cases. If you want to see an example of all the records we support for yourself, just go to app.ens.domains and type in brantly.xyz, and you can see that. All right, so let's also talk about the namespace on ENS. So I've kind of alluded to this a little bit. You've probably heard of .eth. So .eth is the native top-level domain or publics or suffix on ENS, but we're also integrating the DNS namespace. So we've already integrated .xyz, .lux, .cred, .art, and .club. So if you have a DNS name with that ending, you can actually use that on ENS. And I gave the example of Brantly.xyz as an example of that. But we're expanding that to like .com, .org, and .io, and all the main ones here very soon. So stay tuned. So how does ENS compare to DNS? So why would you use ENS at all? Well, ENS has much simpler architecture. So the DNS servers are replaced by smart contracts. ENS has zero downtime. You can't DDoS attack it because you're literally reading it. You could be reading it from your own local node. It's decentralized, more decentralized, censorship resistant, has built-in cryptography and individual ownership, which means better security. And of course, you get all the benefits of programmability and interactivity with other Ethereum smart contracts on the Ethereum blockchain, which of course DNS doesn't have at all. So like the security and censorship resistance properties of ENS make it really good for cryptocurrency, storing cryptocurrency addresses and IPFS websites. And then the fact that that ENS has programmability and interactivity on Ethereum means you can do things like names owned by smart contracts or groups of people like a DAO or multisig. Also that like .eth names are NFTs, which means that they can plug into all the NFT infrastructure that's already built. It's kind of cool. So how would you use ENS? Let's say if you're a developer. Your goal should be that every time a user might otherwise see a cryptocurrency address or content hash, they instead see an ENS name. These computer identifiers, they're great for software. They're terrible for user experience. And users don't even need to know they exist, right? Just like most internet users don't know what an IP address is. They don't even know they have an IP address. They don't know that Google has an IP address. All they know is that they can type in google.com and that takes them to a website. So the primary use case for ENS, I'd say kind of like our bread and butter, is cryptocurrency address forward resolution. So forward resolution means that you supply a name and it resolves to an address. So let's say I'm here in a wallet, I type in an ENS name, the wallet grabs the address, maybe I can verify it if I need to, and then I can send it to that address. And we also have Ethereum address reverse resolution. Now this only works for Ethereum addresses. What this means is that if somebody has your Ethereum address, they can go the other way. They can look up to see if an ENS name is attached to that, and then they can display the ENS name. So this is useful, let's say if you sign into a dApp, and so you sign in with MetaMask, they have your public address, they can look up to see if you have an ENS name and then display that as like your username or something like that. So an example of this, a lot of dApps kind of will show your profile like this. It's very, I think, bad UX. What instead they can do is show your ENS name instead. And if they want to show your address so people can verify if they want to, that's fine, but the ENS name should be primary. So usernames, yes, another thing about usernames is that dApps can give users subdomains for free or if they want to. So you have to pay, there's an annual fee for a .eth name, but a subdomain off that, there is no annual fee. You can have unlimited for free. The only cost is the transaction cost to set it up. So if you have like your dApp.eth, you could give all of your users a subdomain. They just have to pay the transaction cost, and that could be their username, maybe specifically for your dApp, or if they don't have an ENS name. And like universal login and Ethereum and other dApps are doing this. So I mentioned decentralized websites. So we support IPFS hashes. That IPFS is a distributed file storage network, so a Swarm. And then we also support Tor.onion resolution. So that works if you have the Tor browser with MetaMask enabled, and if you type in a .eth name that has a Tor.onion address in the content record, it will resolve and go to that Tor.onion website, which is really cool. So let's say you're on MetaMask mobile. By the way, a bunch of browsers support this. It's IPFS websites natively. We've got Opera on Android, Brave on desktop, MetaMask mobile on mobile, MetaMask extension. The Status mobile app also supports it, and then some other ones as well. It's all listed on our website. Go to ens.domains. You can see all of the browsers that support us, browsers and extensions. So you just type in, your dApp.eth, and there you go. It's like a normal website. We also have this thing called ETHDNS, which is a DNS bridge to ENS and IPFS. So let's say if a user doesn't have Opera or MetaMask or something, and they want to access your decentralized website using ENS, it's not going to work. So we have this thing where if they just simply add .link to the end of the name, then it will resolve like a normal website. So instead of your dApp.eth, they can do your dApp.eth.link, and it will resolve. So an example, like if you go to almonet.eth.link, that's actually a directory, a decentralized website directory, and that should resolve in any normal browser at all. And the way this works is that we own eth.link. So we can direct people through a special server that we have Yes, it is somewhat centralized, but the software is all open source. You can read more about that on our Medium blog. Of course, I mentioned with Tor.onion resolution, you actually try this right now. If you have the Tor browser, only the Tor browser, with MetaMask enabled, then go to DuckDuckGo Tor.eth. I set this up. You're gonna have to put a slash at the end of it. And if you then hit enter, it will go to the DuckDuckGo Tor.onion hidden service. And then we also support traditional DNS records. Like I mentioned, this isn't like a main use case, but it's something we're experimenting with. This just can provide better security for DNS records. Could possibly in the future replace DNS infrastructure, although not for a long time. It could become like maybe the source of truth for the DNS infrastructure. In fact, that's exactly what .cred is doing. So .cred is a top-level domain on DNS. And if you register a .cred name on DNS, they automatically create the same .cred name for you on ENS. And then this is really interesting. The ownership of the DNS.cred name actually follows ownership of the ENS version of it. And then they store the your DNS records on ENS and IPFS. And then they copy them onto their DNS servers, but the ENS IPFS version is the source of truth. This is a really cool project. And then, of course, everything we haven't thought of. So like I mentioned, anybody can create their own ENS record. There's a lot of interesting projects that are using it for their special identifiers like Umbra and other ones as well. So, you know, what have we not thought of? What can you do with it? Feel free to experiment. So thank you very much. Obviously, I'm not taking questions because this is an online presentation, but here's some important links, and thank you very much.
Hi, everyone. My name is Arjun. I'm one of the founders of Connext. Today, I'm here to talk about instant cross-chain and layer 2 communication. Before I get started, I wanted to give like a quick history of Connext. We've been around for quite a while. We built the first ever payment channel hub implementation on Ethereum with SpankChain back in 2018. In 2019, we kind of generalized that and took that to the rest of the Ethereum space, and a bunch of projects like MetaMask and Ujo built really interesting experimental payment flows on top of us. And then this year, we kind of took a lot of the knowledge that we gained from 2019, the user data and user feedback that we gained, and built out Connext V2 and put that live. And V2 basically takes some of the core concepts from V1 and then makes them more decentralized, adds generalized state support, so any kind of arbitrary state transition, and most importantly, improves the user experience slightly. Cool. So that's a little bit of background. Awesome. So jumping into cross-chain stuff. So regardless of whatever vision you subscribe to for the future of this space, whether that's ETH2 with a bunch of different shards, or layer 1, layer 2 with a bunch of different layer 2 options, or even a bunch of different layer 1 chains, we are going to end up in a multi-chain world. And this has some really interesting consequences for user experience. So one of the things that makes Ethereum really interesting to use right now, particularly for things like DeFi, is that the flow for interacting with things like exchanges or things like Uniswap, for instance, as shown here, are incredibly seamless. But it's not really clear how that translates when you have users and DeFi protocols and other kinds of applications interacting with each other across chains. So for instance, what happens if your balance is on the Arbitrum rollup and you're trying to call the Uniswap contracts on the Optimism rollup? Well, what Currently, what the plan is that you would need to exit from the Arbitrum rollup, and this takes time, costs money. It actually takes, I think, it's a 7-day exit period. And then once you get back onto the Ethereum chain, you then need to enter into the Optimism rollup. This, of course, takes away, completely removes the interoperability and composability experience of DeFi that exists right now, and which is one of the main kind of drawing points, and which is what has caused such an explosion of development and experimentation in the space. So let's boil that down into kind of 3 main requirements. We synthesized these a little while back, but what this basically translates to is if we want to keep the same level of user experience that we have with Ethereum today, we need to allow for 3 things. 1, transferring funds across chains in a way where users, and in all these cases, all of this needs to happen in a way where users don't know that it's happening. So transferring funds across chains, either to other participants or to themselves. Users can call contracts on other chains, and this needs to happen in a way where the users aren't actually giving up access to funds as part of that call. And lastly, and this is absolutely the most difficult one, contracts calling other contracts on other chains. So let's see what Connext can do to help with this. So to understand that, let's talk a little bit about how Connext compares to other layer 2 networks. So there's a bunch of different kinds of networks out there, and I think it's a little bit helpful to kind of give context around them just to understand why layer 2 is actually much more diverse than people understand, or people might initially realize. So examples of different kinds of networks, and this is by no means an exhaustive list, are point-to-point network communication networks like TCP/IP, distributed hash tables like Kademlia, and blockchains like Ethereum. And the important thing to note is that all of these things, and especially like all of the implementations of these different kinds of networks, usually use multiple of these other networks in as part of how they function. So for instance, Ethereum's node discovery protocol is built on top of Kademlia, or uses Kademlia. BitTorrent is a combination of Kademlia to actually find where source files are, and then streaming data over TCP/IP. Now, what we kind of think a lot of what we think of within the layer 2 space is to think of scalability as basically doing what Ethereum does, but just faster. And what that usually means is scaling horizontally. So that's kind of what roll-up sidechains and Plasma do, is they take the Ethereum execution environment, and then they just move transactions off of Ethereum into another thing that looks exactly like Ethereum, and just has an independent validator set, or virtualizes the execution environment or something like that. Channels, on the other hand, and specifically Connext, does something a little bit different. So instead of scaling out horizontally to multiple different chains, Connext is a point-to-point network. So it's a little bit more like TCP/IP. And what it does is it allows you to make unbreakable commitments off-chain. And these are basically commitments to be able to call some set of contracts in the future, which can never not be called, even if one of the 2 parties that created the commitment kind of disagree or decide to not show up. Now, what's really interesting about this is that the thing that backs these commitments is just a set of smart contracts, right? On Ethereum, this is a set of Solidity smart contracts. But this could really be it could really be any sort of system where you have somebody proving and verifying that that the funds are actually locked up there, and then how they should be dispersed. So for instance, you could even run Connext on top of a bank account if the bank was the prover and verifier that funds are locked up there and do need to be distributed correctly. And the consequence of this is that you can run Connext on any EVM chain, and not only on an EVM chain, but across a bunch of different EVM chains, because users can have from a whole network structure standpoint, users can have channels running on many chains concurrently. So let's examine a little bit more about what that means, because it's a little bit of a complex concept. In Connext today, if Alice wants to make a transaction to Bob, and she has a channel open with the Connext node, what would happen is that she makes a conditional transaction to the Connext node that resolves only if the Connext node makes a corresponding transaction to Bob. What you'll notice is in that sentence, there is no place where I actually mentioned what chain Alice and Bob are on. the channels that they're interacting with could be on any chain. And in this diagram, we see that Alice's channel multisig, where her funds are actually on chain 1, which could be the Ethereum base chain. And then Bob's multisig is on chain 2, which could be on xDai, for instance. So putting this together, last week we released a demo to the for the Reddit the Great Reddit Scalability Challenge of this exact kind of behavior. So the ability to call to instantly transfer assets across different L2s. And so we built something called Spacefold, which is a really, really simple swap UI that allows you to swap between Optimism, Matic, Arbitrum, Rinkeby, Kovan, Scale, and I'm missing one, xDai. How does it work under the hood? Well, when a user goes to the browser app, what they're actually doing is connecting to a bunch of different channels. Each of those channels is spun up associated with the user's key. And each of those channels can be controlled by the user independently. And each of them is also linked to a Connext node, which acts as a liquidity provider. So if a user has funds on Rinkeby, they're able to swap those funds instantaneously to funds on Scale or on Matic or on xDai simply by sending a transfer to themselves through the Connext node. Effectively, this is kind of like an off-chain Uniswap. Cool. What this means is that Spacefold today and Connext today meets our first requirement. Users can transfer funds across chains without really needing to know that it's happening. And that's one of the cool things that we really, really wanted to show in Spacefold is that as a user, you should never really need to know that you're on a different chain until you withdraw and see your transaction actually be mined on a different block explorer than the one that you expected. And Spacefold also helps us get kind of close to the second requirement, which is the ability to call contracts on other chains. The output of a channel right now on Connext is a call to an ERC20 contract, but there's nothing really that stops that from being a call to any arbitrary contract, so long as we can pass in the right parameters. So at the moment, that's firmly in like the development stage. We know exactly what needs to happen to support this. It's just a matter of time before we can. And then lastly, there's contracts calling contracts on other chains. Now, jumping into this is absolutely out of the scope of this talk because it's really, really complex. But this is definitely a direction that we think is worth researching. And we believe that there are absolutely ways to do this using Connext, possibly at a lower level than what exists, than the kind of EVM execution environment itself, but perhaps directly between validators between chains. If you want to try it out yourself, setting up a Connext node is easy. It's 3 lines of code. And then we also have a guide on how you can do this on multiple chains simultaneously and spin up the Spacefold demo. All of our materials are located on our GitHub and in our docs. You can find them here. And if you run into any issues, absolutely hit us up. We're super responsive on our Discord. Cool. Thank you so much.
Hello, everyone. My name is John Adler, and I'm here to talk about Fuel and scaling Ethereum with optimistic rollups. So let's start with a brief introduction about myself. I'm currently with Fuel Labs, where we're building Fuel, a high-performance optimistic rollup chain. Previously, I was working at Consensus as a Layer 2 scalability researcher, and I created the optimistic rollup design paradigm from that research. So let's talk a bit about the scaling problem, first of all, since obviously, optimistic rollups are supposed to scale blockchains. Bitcoin can do between 3 and 7 transactions per second. Ethereum can do somewhere around 15. Or if we're just considering simple payments, it's more like 30. And meanwhile, Visa can handle 10,000 plus transactions per second at peak capacity. And we would like to increase this number. We'd like to increase transactions per second, or throughput, without decreasing decentralization or requiring new trust assumptions. Obviously, it's pretty simple. If we just trust Visa to process all our payments correctly, then we don't need a blockchain. So we'd like to not insert new trust assumptions. And I said throughput before, which is not exactly scalability. So scalability is throughput divided by decentralization. It's the ratio. And what exactly do we mean by decentralization? Let's find out. So first, let's see, what is the scaling bottleneck? One common talking point is that, for example, EOS is more scalable than Ethereum because it's centralized around 21 block producing nodes. And you might see graphs like you see over here. EOS has 21 block producing nodes with approximately even distribution of some Sybil resistance control mechanism. And meanwhile, Ethereum and Bitcoin have 6 mining pools, 5 mining pools that control the majority of the hash rate, which seems odd because if the number of nodes had anything to do with the transaction throughput, then you would expect Ethereum and Bitcoin to support more transactions per second than EOS's. So it's wrong that the number of nodes has anything to do with throughput. Why? Because consensus is not the bottleneck. So let's see what decentralization is. On Ethereum, we want a non-consensus full node with approximately these hardware specs, a 4-core CPU, 8 GB of RAM, and an NVMe SSD. That should be able to fully validate the chain at a rate approximately 30 times as fast as it grows. In other words, it's able to catch up when it's doing an initial block download. On Bitcoin, our specs are we want a non-consensus full node to run on a Raspberry Pi and a hard disk drive, and that must be able to validate the chain at a rate approximately 100 times as fast as it grows. And in EOS, we want a non-consensus full node with some absurdly high specs that are right here, let's say 64-core CPU, 1 terabyte of RAM, and so on. And it must fully validate the chain approximately 1 times as fast as it grows. So you can't really catch up after if you drop off. So in other words, decentralization is measured by the cost to run a full node. It is not the number of full nodes or the number of nodes in general, let alone full or not. And this is a social contract. Every blockchain has a social contract of how much it should cost to run a full node, and it has nothing to do with consensus. So let's see how Ethereum scaling bottleneck compares to Bitcoin. How does it manifest? Despite the fact that presumably you can say the decentralization of Ethereum is less because the cost of a full node is much more than Bitcoin's, why is it that Ethereum can only do twice the TPS? You can do 15 to Bitcoin 7. And the answer is that it's because of EVM execution. You can do much more complex smart contracts on Ethereum than you can do in Bitcoin. And the second thing is, and this is the big one, is state accesses and state growth. So the Ethereum uncompressed state size is approximately 60 gigabytes nowadays. This can't fit in RAM, therefore you have to put it on an SSD, ideally an NVMe SSD, which means you're going to have very long access times. Bitcoin state, the UTXO set is approximately 3 gigabytes, give or take. So this is kind of where the biggest problem comes in. This is why Ethereum can't do that many more transactions per second, despite having much higher hardware requirements to run a full node. So how can rollups help solve this particular bottleneck? How does it target this particular bottleneck? The rollup design paradigm is essentially you do state accesses and execution off-chain, and you only use the base Ethereum chain for data availability and ordering. And then you ensure that the validity of this data that you're just posting on chain, you can ensure that it's valid using one of three methods. One is a validity or zero knowledge proof. So this is ZK rollups. The other one is fraud proofs plus a timeout. And this is optimistic rollups. And the third is an interactive verification game plus a timeout. And this is what teams like Arbitrum are doing. So why can rollups scale? And there's a star here, which we'll discuss shortly. So with rollups, the consensus nodes, like miners and so on, and also non-consensus nodes, so users, only need to make data available and order it. They don't have to execute transactions. And this is great because you can't have less execution than no execution. Just ordering transactions is basically the optimal amount of work you can do, which is there's nothing, right? You're not executing anything, you're just ordering the transactions. So now where does the can come in from? Where does the can come in? You might have seen interesting numbers like this. You have a 10 million gas limit per block. Each transaction in the rollup, let's say it's aggressively 100 bytes. That's actually quite large. It can be much smaller. The gas cost of call data is 16 gas per byte, and you have a 12-second block time. This gives you 500 transactions per second. And you can look around the internet and you see many estimates of this. But this isn't exactly correct. Why? Because if everyone was just using, let's consider a thought experiment. If everyone was using a single EVM optimistic rollups, then that wouldn't increase scalability. We wouldn't be able to fit more transactions per second if we want to maintain the same hardware requirements and we want to maintain the same rate at which we can catch up. We would still be limited to 15 transactions per second with a single EVM rollup. Some other gotchas, and there'll be a few more gotchas in this slide. You might have seen, comparisons like this, where ZK rollup, the producers of the rollup have to do a lot of work, but verification is very cheap because you just have to verify a succinct proof. You don't have to, fully execute every transaction. And in an optimistic rollup, if you want to be safe, if you don't want to add additional trust assumptions, you do need to fully validate every transaction. Hence why the previous slide we said an EVM optimistic rollup does not result in additional throughput without trade-off somewhere else. And on the surface level, it seems reasonable that this is what validity proofs do. They allow you to prove some exponentially more expensive thing and exponentially less work. But this isn't exactly true. This is not sufficient. Because what happens if all the rollup block producers just go offline and then no one is around to give me a Merkle branch, a Merkle proof that I need to withdraw my coins or to further transact on the rollup? Then what I have to do is apply every single state transition from the rollup's genesis. And it turns out that, let's say, simple balance transfers, Alice just transfers some money to Bob. That's basically 99% just state transition. There's basically no computation being done there, just a simple comparison, which is trivial. So it turns out that in ZK rollups, it is not sufficient to just validate the validity proof. You also, in the worst case, and therefore you must metric your system based on this worst case. In the worst case, you must apply every single state transition from Genesis, and that is not exponentially cheaper. So because of this, validity proofs only scale pure computation with no side effects. They do not scale the number of state transitions. And if you're just comparing, simple Alice transfers to Bob state transitions, then using validity proofs does not provide any additional scalability compared to, for instance, full validation compared to optimistic rollups. Okay, so let's talk about now I spend a lot of time, telling you why optimistic rollups and rollups in general don't provide scalability, or in what cases they don't provide scalability. But let's talk about now how they can provide scalability. What are some benefits of optimistic rollups? So we note that